One of the transformations that sometimes is used in some continuous time signals is Hilbert transform. It's not a big deal. This is just an example. Hilbert transform is an LTI filter which has this unit impulse response. If I plot it, it's going to be a hyperbola like that and so on. So it's not a causal filter, but it is a stable anti-causal. So this is, because not causal, it is not implementable without delay, but you can approximately implement it either in digital domain or analog domain. So the Fourier transform of this particular LTI filter, this is just a normal LTI filter, becomes this function, and this is a sine function which is equal to minus j for omega being positive and plus j for omega being negative. So is this function, if you calculate h of omega, magnitude of h of omega, magnitude of this is 1, magnitude, so this is equal 1. So it has a constant magnitude, and positive frequencies are multiplied by plus j, and negative frequencies are multiplied by positive. So it's kind of like the sign for positive frequencies and negative frequencies are different. So it's kind of like this is the only difference. Now the output, this is called Hilbert transform of x of t. It's just LTI filter, simple LTI filter, which you convolve it with this 1 over pi t. And it is given by this integral. So this is, if input is WSS, the output is also wide sense stationary. And in this example, the cross power spectral density of the input and output is just equal to, you multiply this is equal to xx of omega times h of omega conjugate, and this guy is equal to conjugate of that, and this is what we get. Now if you calculate the power spectral density of the output, you shall multiply this one sx x of omega by h of omega to the power of 2, and for Hilbert transform, this is equal to 1. So the power spectral density of the input and output are identical. In some examples, like for instance for speech signals and so on, if this is a Hilbert transform of these, so x of t, so you convolve it with this impulse response of 1 over pi t, you get this as output, then we call this analytic signal. So that means that calculate for a real signal, calculate this Hilbert transform, and another signal, then the real part is your signal, and then the imaginary part is your Hilbert transform. We call this z of t as analytic signal corresponding to x of t. So this z of t has a one-to-one relationship with x of t. And remember that the Hilbert transform gives your signal back. So for instance, the power spectral density of the analytic signal, because you could see that this is equal to x of t convolved with 1 plus 1 over pi t. And then if you take Fourier transform of that, you get this one, and then your magnitude of that. So the power spectral density of your analytic signal is interesting. So you get this one. So what you see here is that power spectral density of Z has a unit step function. So if you have x of t has a power spectral density here, sxx of omega, Z of t, power spectral density will be 0 at negative frequency. That means that using this Hilbert transform, you can eliminate these guys, and then here you will have the same power spectral density but 4 times. That's it. So analytic signal and Hilbert transforms you don't need to be scared of. So they are very simple.